In astronomy, a lot of the times we talk about the mass of a star. And so we're going to be looking at that. How do you actually find the mass of a star? And also, how do you find the mass of a black hole? That's going to be the next series of videos here. So first of all, this question then, how do you weigh a star? I mean, if you take a star, let's just, let's say draw it here like this. And I mean, this is how I used to draw stars as a little kid. I'm not a very good artist, clearly, but here we go. So if I take this sort of star here, I mean, I can't really put it on a scale, can I? I mean, I can't put it on a scale. I can't find out how much it weighs. So that's difficult to do. I mean, how do we do it then? I mean, if this here is the scale here, you're going to put it on. I'm not sure. This here doesn't really look like a scale, does it? But in any case, it's not that easy. I mean, there are lots of methods of doing it, but the main thing we're going to be concerned with is this. We're going to use the laws of physics. So we're going to use what we know about physics in order to infer its mass. Because we can't actually go there and put it on a scale. And even then, a scale wouldn't really make much sense if you think about it, because a scale uses gravity and there's all sorts of issues there. But we're basically, the idea is going to be we're going to use our laws of physics to infer. In other words, we're going to get its mass using what we know about physics so far. Clearly, if we're wrong about physics, then we're wrong about the mass. But the good news is this method has been shown to work very, very well. So the way I'm going to show you, I mean, there's lots of ways of doing it, but we're going to use, well, actually, we're going to use Kepler's laws. We're actually going to use Kepler's third law, but I figured it's a good opportunity to just show you Kepler's three laws. So Johannes Kepler, a long time ago, this is in the 1600s, he was actually an assistant to a sort of a grumpy Danish scientist named Tycho Brahe, although people normally write it as, here, I'll write it like this. So he was assistant to a Danish guy named, I mean, a lot of people call him Tycho Brahe. But if you're a Dane, they pronounce this Tycho Brahe. In any case, this sort of grouchy guy right here, he was doing a lot of empirical measurements. He would look up at the sky and notice where everything was. So he would sort of write down the positions of everything. And he didn't really use a telescope. He mainly just used a big, giant protractor, basically. So he would sit, you know, in his castle, let's just say. So here's his castle. I'm drawing a really bad version of a castle here. But let's just assume he's got this big device here that's going to measure the angle of things. And he'd look at, you know, where stars were and sort of write down where they were. And he had an assistant named Johannes Kepler. And he actually then used this data to do something useful with it. Now, these laws are empirical. And what that means is they weren't necessarily grounded on any sort of physics rules. They were just what he noticed. So he noticed three things about orbits of things. So this here is what we noticed, not just about stars, but of course about things that go around stars. So things like planets. And so what he noticed then about orbits was this. Well, the first one is that planets orbit. Maybe I'll write this in blue here. So I'll say this like this. So the planets are going to orbit, or planets, let's say, have elliptical orbits. And with the star as a focal point. Now what this means, that's sort of the first law, essentially. So what goes on then is, let's just say you're looking at the sun here. Let's just say, well, actually, let me just draw this. I'll draw an orbit here. So let's just say this here is going to be some sort of ellipse. Now, an ellipse is like an oval, so it's not a pure circle. Actually, it turns out a circle is just a special form of ellipse. We can talk lots in mathematics about ellipses and what we call ellipticity. We have a little constant e we use to say sort of how oval this is. So things can be really, really round. It can be really stretched out. But it turns out orbital things are elliptical. That means they follow these sort of paths. And the important thing is, at least in mathematics, when you have an ellipse, it turns out you have two special points here. I don't know if you've ever actually tried to draw an ellipse, but it's actually kind of cool. If you actually, I did this usually with my students, I would put a tack, like you sort of nail something to the wall here and here. usually use like a thumbtack or something, then I would use a piece of string to join together this piece and this piece. And so, for example, then I could, have this piece of string sort of joining these 2 points together. What I would do then is use this piece of string and use my pencil inside a string to basically just carve out, just sort of move the string around in the sort of try to do a circle. And it turns out that is a perfect way to draw a perfect ellipse. So what will happen is this. You have these things called the focal points. So I'm not going to go into the math of it, but this is basically, how a circle has a center? Well, an ellipse has 2 focal points here, or sometimes they're called foci. I've heard people call it foci. In any case, that's what those are here. Those are the focal points. And it turns out that the star is going to be one of them. So maybe this right here is the sun. Let's just say, so maybe that's the sun. If that's the case, then that right there is one of the focal points. You might wonder then what happens with this one? Well, it's just an imaginary point here. So we're essentially going to sort of forget about it. So I'm just going to erase this and say, there we go. It's going to look like this. So that means that the path that this planet will follow, maybe it goes around like this right here. It'll go around in this sort of elliptical path here. Now I'm going to show you a little animation here. Once again, it's using this awesome University of Colorado program called PHET. And this one is called My Solar System. I'm just going to use the very simplest thing right here and just show you. Okay, so here's what we have. And although these animations look simple, there's some really cool physics going on, and they do lots of calculating here for us. So what's really happening then is this. This little planet is going around the star in the middle. What I want you to notice, though, is that the star, a lot of people just draw orbits as if the star stays still and the planet just goes around it. But that's not the case. Turns out later on that's going to be really important for us, that the planet goes around the star. Technically, the star is perturbed by the planet. If you notice, they both sort of orbit each other around a common center of mass, which is going to be somewhere in the middle. Well, not in the middle here, because this one's way more massive. Now, of course, I could take a look at a better one here. I can take a look at one. These are theoretical ellipses, I think it is. Yeah, if I do ellipses, that's a fun one. Now keep in mind, these orbits are a little bit dangerous because all 3 of these ellipses are going to run into each other, and that would be very dangerous if you're a planet. But take a look at it. So you can see this center one here is very circular. The next one is more elliptical. In other words, it's more oval. And the green one is even more stretched out. What I want you to notice as well is look at their speeds. Look what's happening. This one right here inside is going a pretty constant speed, and it's going fairly fast. This other one right here is going slower at the end, you notice, and then it comes close and it speeds up and slows down again. And that's even more extreme for this green one. Turns out these are realistic orbits. And what I mean by that, so actually I'm just going to close that because I won't need it anymore. What I mean by that then is that this is going to help us actually for number 2 here. So number 2, it says something about that a line, this is sort of a technical thing here, so a line joining, and this becomes a little bit complicated looking, joining the planet and let's say the star. So, okay, so if we take a line and we join the planet and the star, we're going to say it sweeps out. This is this sort of weird thing here. It sweeps out equal areas in equal times. Now this one seems a bit, whoops, not equal times. This one might seem totally crazy. So let's take a look again at what happened before. Remember I was showing you that animation where they were going faster when they were closer to the center. So let's say this here is the star here. That's the sun, let's say. So what happens is, let's say we join a line. Let's say we look at this planet from here, and let's say we look at it over a period of, I don't know, let's say 20 days, let's just say. Let's just say 20 days, it goes from here. Let's assume it goes this way. Let's say after 20 days, it maybe goes this far. So maybe it goes from here, and 20 days later, it's over here. Well, that means if we made a line that's joining together, in other words, joining the star and the planet here, and the star and the planet here, if we found that area, we can call that area A1. That's sort of the area here. And then we can consider another time. So what if way over here we were looking at it, let's say here, and let's say 20 days later, so the same amount of days, whatever number of days this was, let's say it was 20 or 30, it doesn't matter. Whatever amount of days you used in order to go from this one to this one, use the same amount of days to go from, let's say another point, maybe from here to here. Well, it turns out, if you remember these orbits before, it was going faster here, and it slows down as it gets out here. So maybe that same amount of time later, maybe it only went this much. Well, it turns out I can still make a line joining those together, so I can attempt to do that. I'm not very good at drawing straight lines freehand, but we'll see if it works. That wasn't too bad. Let's say I calculate that area. Although it didn't go as far, there's still a bigger distance in here. Turns out if you calculate that area, let's say A2, well, you're going to see that A1 equals A2. That's actually pretty neat. So again, Kepler figured this out in the 1600s. This guy figured this out. There wasn't necessarily a reason for it. He didn't necessarily know why it had to go faster here and slower here. He just knew that it did. And so I have this, I think it's a really funny, simple joke here from XKCD. This is one of his earlier ones, but it's awesome. He says, "Nice store. How do you keep the floor so clean?" He says, "Oh, we hired this dude named Kepler. He's really good, hard worker, doesn't mind the monotony. He sweeps out the same area every night." Ha ha ha. That's because these things sort of sweep out the same area. But that's a really bad joke. Let's do Kepler's third law. Now this one is more complicated. The basic way to say it is this, that the period, let's say here, the orbital period, and let's say squared, is proportional to the, and in this case, let's say the orbital radius. This isn't entirely true. I'll talk about that in a second. The orbital radius, in this case, it'll be cubed. What I mean by that, now the reason I'm saying it's not exactly the case, is that we're going to be making some assumptions here. Okay, we're going to actually be assuming some things. The way it really works, I should technically say, instead of orbital radius, I should really say semi-major axis. That is actually really what it is, because the radius is not entirely true. And that's because we have ellipses, and in an ellipse you don't have the same distance. I mean, it's not a circle, so you can't say that an orbit has one radius, because it's not a circle, it's an ellipse. That means it has a different distance from the star. I mean, look at this. From here, its distance from the star is maybe this short distance, but over here it's a lot longer. So in mathematics we have something about, we could say it's the semi-major axis, and we define it as such. But what we're going to do is we're going to simplify things. We're going to actually say, okay, forget about this semi-major axis stuff. We're actually going to consider circular orbits. And if we assume it's a circular orbit, now this is a big if though, but if we assume it's a circular orbit, then we can say this, that the period squared, that's what this is. See, the orbital period, that's t. Okay, that's the period right here. That's this value right here, t. T squared is proportional to, we could say r cubed. Now we're going to say a radius, but it's really a semi-major axis. What do I mean by proportional to? What this means is that t squared equals some stuff, which we don't really know, times r cubed. So this is what Kepler figured out. He knew that, well, you could do ratios of things then, and that was a really useful part. So if you knew something about the Earth, then you can compare it to something else, and away you would go. So this is sort of where Kepler stopped. He said, well, they're proportional, but he didn't exactly know what number should go here or what should really be here. So what we're going to do in more detail now, in the next video, we're going to be actually deriving the Kepler's third law, and we're going to use that in order to tell us the mass of the star.